Let's take a look at the next example. In example 4, suppose we have a sample of size 100. We're asked to find the probability of a sample mean being greater than 24.3 if the mean of the population is 24 and the standard deviation is 1.25. And as a follow-up, they want us to answer the question of whether or not this sample mean would be considered unusual. Well, probability, this is the kind of thing that we focused on calculating back in 5.1 and 5.2. We know how to calculate probabilities within a normal distribution via our normal Cdf function in the calculator. First of all, when we go to construct the sampling distribution, let's first begin by computing mu sub x bar and sigma sub x bar. We know that mu sub x bar is equal to mu, so if mu is 24, then mu sub x bar is 24. Our standard deviation of the sampling distribution is going to be sigma divided by the square root of n. That's 1.25 divided by the square root of 100, which is equal to 0.1250. Now, before we can use our normal CDF calculations, we have to understand and know why this particular sample distribution is going to be normally distributed. And the answer to that is because of the sample size. Here, we know that n is 100, which is greater than or equal to 30. So because we have a large enough sample size, that means that our sampling distribution will be a normal distribution. So if we kind of do like we did in the last example, let's do our rough sketch. This is going to be our sampling distribution. We want to do just as we did in the previous sections where it's a good idea to draw that sketch. Here the mean is 24, and we're asking the probability that the sample mean is greater than 24.3. Well, 24.3 would be to the right of 24, so we would shade everything over here. And now, because we know it's a normal distribution, we can use the normal CDF function. So we go to our calculator. It's going to be second distribution, normal CDF, choice 2. The lower bound of this region, it goes as far to the left as 24.3. So 24.3. It's going to go all the way to the right, like towards positive infinity. So that's going to be our 1 second comma for the E99. And this is the thing, especially in this 5.4, that you have to pay very, very close attention to. The probability that we're computing isn't the probability that a single value is greater than 24.3. It's the probability of a sample mean. Remember that sample means these are the objects that naturally belong to the sampling distribution. Therefore, you need to use the mean and the standard deviation of that sampling distribution. So whenever we do our lower bound, upper bound, and then mean standard deviation, the mean that's going to go here technically is mu sub x bar. That's going to be 24. And the standard deviation should be sigma sub x bar, which is 0.1250. Go ahead and hit enter. And we would compute it to 4 decimal places that the probability is going to be 0.0082. 0.0082. To answer the follow-up question, would this sample be considered unusual? Absolutely. It's a probability that's less than the benchmark of 0.05, which is our cutoff for unusual events. So the thing that's kind of nice about this section, once you get a grip and understand kind of what sampling distributions are, a lot of the probability calculations are done just like we did back in 5.1.5.2, but just keep in mind that you need to use mu sub x bar and sigma sub x bar in the normal CDF whenever you're computing the probability on a sample mean. Let's take a look at another one. In example 5, it says during a certain week, the mean price of gasoline in California was $2.99 per gallon. We're going to take a random sample of 38 gas stations. It's going to be drawn from this population. What is the probability that the mean price for the sample was between $3.01 and $3.03? And we're going to interpret the results. And let's assume that the standard deviation for all gas prices that week was 0.049. So again, the thing that's going to kind of tip you off, a lot of these problems are going to read the same. The moment you hear that buzzword sample size, the only place in Chapter 5 at all where we discuss sample sizes was in Section 5.4 right now. So that's going to kind of tip you off that you're going to be looking at sampling distributions. Immediately then you'd want to calculate mu sub x bar and sigma sub x bar. Mu sub x bar is equal to mu, so that's going to be 2.99. Sigma sub x bar is equal to sigma divided by the square root of n. That's going to be the 0.049 divided by the square root of sample size of 38, which is 0.0079. And we want to compute the probability that a sample mean, probability that the mean price for the sample was between 301 and 303. That is going to be in the sampling distribution. Before we use the normal CDF, we have to see whether or not we would expect our sampling distribution to be normal. And once again, we have a large enough sample size here. We have a sample of size 38, which is certainly more than our benchmark of 30 or more. So we know that the sampling distribution will be normally distributed, which means that we can use the normal CDF function. Again, it's a good idea if you want to go ahead and sketch that curve. We'd expect a bell-shaped curve with a mean corresponding to sigma mu sub x bar, which is 2.99. If we look at our left bound, the left bound on this one, second distribution, normal CDF, our lower bound would be the 3.01. The upper bound would be 3.03. Mean of 2.99. Standard deviation. I'm going to do something a little bit different here than what you see in the notes. One of the things that especially will happen as you start to type your answers in and work within my stat lab is this value I have here, this 0.0079, that was rounded to 4 places, okay? If you round your sampling standard deviation to 4 places, more often than not, your final answer should come out rounded correctly. But because this number was actually a rounded value itself, what I would like to do is maybe include a few more digits, or as kind of a shortcut technique trick, you can actually enter this calculation part in to that last entry part where they're asking for sigma, and then that will float all of the digits and eliminate any potential for round off error. So I'm just going to put it in as 0.049 divided by the square root of 38, and I don't have to worry about rounding being an issue. If, as you're working through your homework in section 5.4, if you feel like you're doing the problems correctly, but if for whatever reason they're coming back incorrect, email me. It could be just a matter of rounding error associated to sigma sub x bar, and I'd be more than happy to take a look at that for you. Let's go ahead and hit paste. We should find that this probability would be 0.0059, so 0.0059. And as I mentioned a moment ago, because I actually took a more accurate value from sigma sub x bar, the answer I get, which is 0.0059, is even more accurate than this 0.0057 answer. So just that little difference there, especially if it's my stat lab, as most of you probably realize, might be enough to throw it off and maybe have it come out incorrect, certainly if they were asking it rounded to 4 places. What's the interpretation of this? Well, we would expect approximately about 0.59% of the samples of size 38 would have a mean price between $3.01 and $3.03. Let's take a look at another one. In example 6, they say that the mean height of men in the U.S. aged 20 to 29 is 69.9 inches. We're going to take a random sample of 60 men, and let's assume that the standard deviation is 3 inches. What is the probability that the mean height for the sample is greater than 70? So we're again asked for a probability about a sample mean. So that's going to be from the sampling distribution. We want to know mu sub x bar and sigma sub x bar. Again, mu sub x bar is going to be equal to mu. That's the 69.9. Sigma sub x bar is going to be equal to sigma divided by the square root of n. That's 3 divided by the square root of 60, which is approximately 0.3873. We would again know that the sampling distribution is normal because our sample size is large enough. We have 60. So we can go ahead and draw a bell-shaped curve. The mean would correspond to the mu sub x bar, which is 69.9. And we want the probability that the mean height is greater than 70. 70 is a little bit bigger than 69.9, so it would lie to the right. And greater than would mean shade everything to the right of 70. That will help us get our lower bound and upper bound in. We would go second, distribution, normal CDF. The lower bound would be 70. The upper bound is going to be positive infinity, which we use as 1 second comma 99, 1e99. The probability on a sample mean, we need to use mu sub x bar, which is 69.9. And then for sigma, we need to use sigma sub x bar, which I'm going to put in the exact value, the 3 divided by the square root of 60. Go ahead and hit enter, and we would get that to 4 places. This should round to 0.3981. So 0.3981. Here it's kind of fortunate that whether we use the exact answer or whether we used a slightly approximated one, we still got the same answer to 4 decimal places. Let's take a look at the follow-up part B. Assume that the heights given above are normally distributed. So again, assume that the original population itself had values that were normally distributed. The question asks, are you more likely to randomly select a man whose height is less than 65 inches, or are you more likely to select a sample of 7 men with a mean height less than 65, and then to explain? So if we're asked to judge the likeliness of 2 events, we want to compute the probabilities. Let's start with the probability of selecting a man with a height less than 65 inches. That's a probability on a single individual, which is an element of the original distribution. So if I want to compute that probability, I'm going to use my normal CDF, second distribution, normal CDF. If you want to, you can sketch it out. But less than 65 inches, it's going to go all the way to the left. That's going to be negative 1e99. The right bound is going to be 65. Because this belongs to the original distribution, we need to be using a mean equal to mu and a standard deviation equal to sigma. So this is going to be 69.9, and we're going to use the 3.0, which was the standard deviation of the population. We go ahead and we hit enter, and we would see that to 4 decimal places, that would round to 0.0512. So that's the probability of selecting a single man whose height is less than 65 inches. Let's now go ahead and calculate the probability that we get a sample of 7 men whose mean height of the sample is less than 65 inches. This probability is now the probability of a sample mean, so that's an element that belongs to the sampling distribution. Okay. So we're going to do second distribution, normal CDF. Again, if you sketch it out, less than 65 means it's going to go all the way to the left. That's going to be negative 1e99. The upper is going to be 65 if you draw your graph. And now because it's a value in the sampling distribution, we need to use a mean equal to mu sub x bar and a standard deviation equal to sigma sub x bar. The mu sub x bar value is always the same as mu, so it's still going to be 69.9. But now in this case, we're looking at a sample of size 7, which means that sigma sub x bar should be equal to sigma divided by the square root of n. That's going to be 3 divided by the square root of 7. Now, before we go any further and compute this, let's take a step back for a moment. How do we know that we're allowed to use the normal CDF function? In other words, how do we know that this particular sampling distribution is going to be normal, because after all, we only have a sample of size 7. Well, the reason why we're able to do that is this line right here. They tell us that assume that the heights of the men were normally distributed. So what that means is we're beginning with a population that was already normally distributed. And according to the central limit theorem, that means that we can take a sample of any size and this corresponding sampling distribution will also be normally distributed. So this is going to work. Our sampling distribution here is normal, so we can trust and rely on the normal CDF calculation. If we go ahead and hit enter, we would get a probability of about 7.7-ish, E -6. Remember that scientific notation? That means take the decimal spot and move it 6 places to the left. 1 place would go around the 7, and then you would need to go 5 more places, so you need to do 5 zeros. So this would be 0.00000. There's your 5 zeros, and because I was more accurate than the notes here, this would actually bump this up to an 8, so 0.000008. Obviously, between the two, which probability is larger? Well, the first one was larger, which means that we are more likely to select a single man whose height is less than 65 than we would be to select a sample of 7 men whose mean height is less than 65. Okay. So again, I love this problem because it really kind of shows you the different probabilities that are computed. The first thing they were asking for was a probability in the original distribution. So our mean was mu, our standard deviation was sigma. The second part of it, we needed to compute a probability in the sampling distribution, and there we needed to use a mean of mu sub x bar and a standard deviation of sigma sub x bar. Okay. Intuitively, it kind of makes sense after all if you look at it. Just looking at the probability of getting a single person, a single man whose height was less than 65 inches, was not quite, but very close to being unusual. So to ask to get a sample of 7 of them and still have the average height of all 7 of them remain less than 65 inches, it makes sense that that should be a very, very unlikely, very unusual event. We have one last question in this section. This is example 7. This is kind of a cautionary tale, if you will. They tell us that the mean price of 7-inch tablets on a website is $200 with a standard deviation of 60. Random samples of size 20 are drawn from the population. What is the probability that the mean price for the sample is less than 175? So we read it through. It sounds very similar to the last bunch of examples we've already done. But one key difference this time is this is not a probability that we can actually compute with what we've learned in this chapter. We can compute, you can calculate mu sub x bar, you can calculate sigma sub x bar, but there's no guarantee that the sampling distribution is going to be normal. And the reason for that is nowhere do they tell us that the heights of these, or the price of these tablets is normally distributed. So we cannot assume that. So we don't know that whether or not we're sampling from a normal distribution. Furthermore, we have a small sample size. We don't have 30 or more. So the central limit theorem is not satisfied. Therefore, this would not be something we could actually compute with the method that we would learn in our class.